The concepts of local maximum and minimum values encountered in Chapter 4 extend easily to functions of two variables of the form z equal f of xy. Now this figure shows a surface defined on a domain D in the xy plane, and the surface has peaks and it has valleys. So there's high and there's low points. So here we have a local maximum and an absolute maximum. It is the highest of all the high points. Here we have a local minimum. Here we have a local minimum and an absolute minimum. And here we have a local maximum again. Okay, so what we want to do is to be able to locate and classify the points when we're on a surface. Okay, a function has a local maximum value at AB if f of xy is less than or equal to f of AB for all the x in the domain in some open disk centered around AB. In other words, there's a local maximum at this value if it's the highest value in some region around AB. A function f has a local minimum at AB if it will be the lowest value for all the points xy in an open region around the point AB. So local maximum or local minimum values are also called local extreme values or local extrema. So extrema just refers to the maximums or maxima and minima values. Okay, so now if f has a local maximum or minimum value at a point AB and the partial derivatives exist at AB, then the partial derivative at AB with respect to x and the partial with respect to y evaluated at AB must both be 0. Now, not every point where those partial derivatives are 0 will be maximums or minimums, but those are the candidates. Those are the places where there will be, if there's a maximum or minimum value, it will occur at one of those points. So what we'll do first is we're going to find those critical points, just like you did when you were doing it in Calculus 1. An interior point in the domain of f is a critical point if either the partial with respect to x and y are both 0, or one or both of those partials does not exist. Okay, the same thing you did back in Calculus 1. You first looked at the x values where they made the derivative 0, or you looked at the x values where the derivative was undefined. So here we're going to look at the points where the partials don't exist or where both partials are equal to 0. Those are your candidates for local maximums and minimum values, and we call those critical points. So now we just need to be able to classify those points. So let's look at an example. Find the critical points of this function. Okay, so the first thing we'll do is we're going to look at the partial derivatives. I want the partial with respect to x. Now I'm just going to go ahead and use the product rule. I'm taking the partial with respect to x. There's x's here and here, so this part's just a constant. So I'll have y plus 3 now times, since x is involved in both of these two factors, I need the product rule. So I'm going to have xy times the derivative of x minus 2 with respect to x, so that's 1, plus x minus 2 times the derivative of xy, which will just be y. Now I notice there's a y in common with both of these two terms, so I'm going to go ahead and pull that y out, and I'll have just an x plus x minus 2. So that'll give me y plus 3 times y times 2x minus 2. Or I'll take the 2 out. I'm just moving the y to the front, and then I'll have x minus 1. So that's the partial with respect to x. Now the partial with respect to y. Now looking at that, anything with just an x is a constant. So this is just a constant. So now this term and this term factor both have the y in it, so I'll need the product rule. So I'll have xy times the derivative of y plus 3, which is 1, plus y plus 3 times the derivative of xy with respect to y, which will be x. And notice I have an x in common here and here, so I'll pull those out. I'll have x times the x minus 2 that's already in front, and then I'll have a y plus a y plus 3. So that'll be x times x minus 2 times 2y plus 3. Now, you want to find where both of these are equal to 0. So I want to know what values make the partial with respect to x 0 and the values that make the partial with respect to y 0. Okay, when you're solving this kind of a system of equations, take one of the equations first. I'm going to take this one, and I'm going to find all possible ways that that left side can be 0. So I'm going to have 3 cases. Case 1, where would be the y would be 0. Case 2 would be the y plus 3 is 0. In case 3 would be that x is equal to 1. So how can this factor, and this factor all be 0? Okay, so now once I've narrowed that down, those are the ways that the first equation could be 0. Now you want to use those in the second equation and then find out what's true about the other variable. So assuming that y is equal to 0 and now incorporating that into this equation, I'll have x times x minus 2 times 2 times 0 plus 3. Well, that's going to be true when x is 0 or x is 2. But y had to be 0 for that case. So that means we have the points 0, 0, or 2, 0. Okay, case 2. If y is negative 3, now plugging that into the second equation, I'll have x times x minus 2 times negative 6 plus 3 equal to 0. So I've got negative 3 times x minus 2 equal to 0, which occurs when x is either 0 or positive 2. So when y was negative 3, x had to be 0 or 2. So that gives me the 2 points, 0, negative 3, and 2, negative 3. Okay, now my third case, x equal 1. Plug that into the second equation. I'll have 1 times negative 1 times 2y plus 3 equal to 0, which means then that 2y plus 3 is 0, which means that y is negative 3 halves. So when x is 1, the y has to be negative 3 halves. And you have 5 critical points. So next we want to be able to take those critical points, which are the candidates for the local maximums and minimums, and evaluate those and determine whether they're local maximums or local minimums or neither.